5 flat Earth, globe Earth explorations to do on or around the June solstice. Get yourself outside and make some measurements. I will say this is a revision of a video that I made 1 year ago. So this is, as I'm recording this is June of 2020. So there are 5 explorations that you can do, or at least that I recommend. 3 of them are very specific to the June solstice, and 2 of them you can do any day of the year. We're going to describe these in detail in the coming minutes. Now, all these things are involving very, very carefully observing the sky. And so the first main objection is you can't tell the shape of the floor from the shape of the ceiling. And this is true. In this theater, the floor is sort of dome-shaped, but the ceiling is flat. Here, the floor is flat, but the ceiling is dome-shaped. Here, the floor is angled, and then the ceiling is dome-shaped. So yes, you cannot tell the shape of the floor from the shape of the ceiling. That is true. But my response is that no matter the shape of the Earth, whether it's flat or it's a globe, the sky will always appear to be a hemisphere. In other words, the shape of the sky always appears to be a dome, regardless of the shape of the Earth. All right, and in none of my do-it-yourself explorations do I ask people to determine the shape of the sky. I never ask you to do that. I ask you to examine other elements of the sky, but not its shape. The shape is always going to appear to be a hemisphere. And I recorded a whole video on this about a month ago. The sky is a dome. Okay. Second main objection is that the sun, moon, and stars and planets are just lights in the sky. Okay. Oftentimes you hear people say they're just lights in the sky. So let's tune yank the cable out of the back of a television set, or let's tune it to a station between the stations, and we just get white noise static. Now, what if we imagine that that was the night sky and we're pointing our telescope at it? Are there no patterns? There are no repeating cycles? Is it just random, unpredictable? And I hope you would agree that, yes, the television is random, the static is random, but the actual night sky is not random. There are definitely positive patterns that you can pick up by examining the sky. All right. And so, for example, if you're standing in Madagascar and it's a sunny day, you could say, I could see the sun just fine from here in Madagascar. So you can definitely look up in the sky and examine the sun. All right. The third main objection is we don't know exactly what the sun, moon, and stars are. All right. And this is fair. I mean, there's some people who, they've proposed theories of exactly what their composition is. But let's say you don't believe them. You don't know exactly what the sun, moon, and stars are. So here's an analogy for you. I'm in eastern Pennsylvania, and I don't know if this is a Pennsylvania Railroad thing or if this is a certain freight line, but I see these signals all over the place whenever I'm driving near railroad tracks or riding a train. I see these signals all the time, and I've to this day I do not know what these signals mean. Okay, and if you think about it, if both signals are operating and they both have 3 lights, there's like these different possibilities, and so I could argue I don't know what these signals are. Now, does that mean that it's not knowable? Does that mean that I couldn't carefully make a study? Now, obviously, I could Google it. I could look up the manuals, right? But let's say I just want to use observation. Just using the powers of observation, could I figure out what these signals mean? And the answer is yes. All I have to do is look at what the behavior is of trains when they come to these signals. Do they come to a dead stop? Do they proceed slowly? Do they come by with full speed? Do they stop and then proceed slowly? I mean, there's a bunch of possibilities of what a train could do, and I could then make some observations depending on what signal I see and depending on the train's behavior. I could make an observation, even though I don't know what these signals are. All right, so these are the second and third objections, and the responses are, can you study these lights in the sky? I mean, yes, they're lights in the sky, but can you observe them and study them? And again, all of my do-it-yourself explorations will return results, whether the Earth is globe or whether it's flat. Okay, you can make these careful observations. There is nothing preventing you from making these observations other than cloudy weather. Now, what if it's not exactly the date of the June solstice? And like I said, I'm recording this on June 19th. Tomorrow is June 20th of the year 2020. And so we'll see that you have a little bit of latitude. So here's a graph of the subsolar point at solar noon. And this graph is accurate on both globe Earth and flat Earth models. So if it's the date of the equinox, either the March equinox on the left or the September equinox on the right, I think everybody agrees, globe Earth, flat Earth, everyone agrees that the sun is directly above the equator. All right. And then if we have the December solstice, I think also everybody agrees that the sun is directly above the Tropic of Capricorn. That is the southern tropic. So here we are focusing on the June solstice, and that is when the sun is directly above the Tropic of Cancer. And I think everybody agrees that, regardless of the shape of the Earth. So the question is, how close is the sun to exactly the Tropic of Cancer? And again, this takes place on or around June 21st each year, a little bit of plus or minus. It's usually June 21st. The year 2020, it's going to be June 20th. So that's Saturday, June 20th is the date. But if you take a look at this area of the graph, this is 2 weeks before and 2 weeks after. So within 2 weeks or so of the solstice, the sun is really, really close to the Tropic of Cancer. And so I would say all these explorations would be perfectly fine to do within 2 weeks of the solstice. So it doesn't have to be on the exact date. All right. So again, these are these 5 explorations. We're going to go through them in a little bit more detail. And we're just going to take a really quick, breezy look. The actual videos describing these are between 15 and 30 minutes long. So we're just going to take a look at them very quickly. Starting with the angle of elevation of the sun. Now this is at solar noon. Angle of elevation of the sun. And the equipment you need is very, very simple. You just need a solar clinometer, and you can make one for $1. You get a plastic protractor from the dollar store, you get a pencil, a piece of cardboard, a piece of string, and a weight to put at the end of the string. All right. And the idea of how you use the clinometer is at solar noon, you point the pencil at the sun till the shadow of the pencil disappears from the cardboard, and then just take a reading. And it's really easy if you have a cell phone, you literally photograph. You could photograph the reading. You don't have to put your eyeball up against the scale. You snap a picture when you've got everything lined up. And then you got a measure of the angle of the sun. You don't even need to see the horizon. You could be in an area where you can't even see your horizon, and you don't need to know where the horizon is to get the angle of the sun. Now, if the Earth were a globe, this angle will be 23.4 degrees northward from where it was on the equinox. And I've got the whole video explaining that in much greater detail. If the Earth were flat, you're going to have to use a little bit of trigonometry, and there are some assumptions baked in, and you're welcome to change those assumptions and redo the math. All right, but the angle is going to be dependent on your latitude, whereas on the globe Earth, the angle is not dependent on your latitude, as long as you know where the equinox sun was. All right, and so there's a summary of the math, more details in the actual video. So let me just explain this just in a slightly different manner. So if the Earth were flat and the sun is traveling above the equator on the equinox, on the June solstice, the sun is above the Tropic of Cancer. So let's take a side view from the North Pole on the left to the ice wall on the right and the equator in the middle. So again, on the equinox, the sun is directly above the equator, and you can have a bunch of observers all over the Earth taking readings, taking observations of the angle of elevation of the sun on the equinox. And the math is pretty straightforward. But now the sun is above the Tropic of Cancer on the June solstice. So what you're going to do is you're going to be comparing those two angles, right? You're going to compare those two angles. And I hope you see that the further you are from the equator, the angle will have a different difference depending on where you are. So that's going to be a big clue that the Earth is flat versus the Earth is a globe. If the Earth were a globe, on the other hand, again, let's take a look at the equinox. The sun is 93 million miles away to the right. So the sun is directly above the equator. Everybody measures their angle. But then on the June solstice, the Earth is tilted 23.4 degrees towards the sun, which means that everybody's angle is going to be exactly 23.4 degrees northward, for no matter the observer. So that's going to be a big clue when you make your measurements, whether the Earth is flat or whether it's a globe. All right, and again, there's a review of the math. Go ahead, watch the complete video, and it'll explain this in much more detail. Let's take a look at the second exploration, which is the azimuth of sunrise and sunset. Now, azimuth simply means like the cardinal direction, north, south, east, or west, but the exact angle, the exact number of degrees where, north is 0 degrees, east is 90 degrees, etc. All right, azimuth of sunrise and sunset. So what you need is a way of measuring the azimuth of sunrise and sunset when you're out there in the field. Okay, so you could make a cardinal azimuth tool. This is made out of literally 4 yardsticks, where one of the yardsticks can kind of swing around and point. And there's a little scale you see there. So this is me out in the field. I have taken the pointer away just so you can see the scale a little better. But there's me out in the field about to measure, the actual angle. Now, there's another way of measuring the angle, and that's it. If you have landmarks where you see the sun, like if you're out in the middle of a field, or at the beach, maybe this wouldn't work. But if you're, in a town or a city, and you can line the sun up with some landmarks, you might be able to use that to figure out your azimuth. So, for example, let's say the sun was setting directly along this street. This street is at some angle. I'm just going to pretend that this is Oak Street. Okay? Well, you could literally measure the angle of that street and then figure out the azimuth of, say, sunset. All right. Now, here's another picture. Now, this isn't exactly at the moment of sunset, but you get the idea. Like, let's say the sun was a little bit further down. Now, we're looking in Miami. We're looking westward in Miami across the MacArthur Causeway. All right. So there's the Google Maps. There's the causeway over that body of water. And so what we need to do is we need to figure out the exact location of that sunset. So what did I say? Line up the sunset with a landmark. Well, if you take a look at the sun, it is behind that building right there. So I'm using Google Street View. I'm now on the MacArthur Causeway, and I really need to find the identity of that building that is directly behind the sun. So I'm using Google Street View, and I've located the building, but I need to get in closer. So a little bit of sleuthing, and I determined that was actually the Palace Condominium in Miami. Okay, we're looking at it sort of edge on. It's a very famous building in Miami. So now we're just going to use the distance tool to connect where the photograph was taken with this building. Okay, so that's where the Icon Condominium Association was where the photograph was taken, and now we can measure that angle. So here's how you could do it. You could literally take a screenshot of your Google Maps, knowing that north, is directly is up on your monitor screen. And what I did is I literally took a piece of clip art, a 360-degree protractor clip art, and I placed it over here, and then I turned it transparent using, some graphics tools. I just turned the protractor transparent, and then I'm measuring that it's a 249-degree azimuth. So regardless of how you've measured the real-world azimuth of sunrise and sunset, again, this requires you get outside and measure this stuff in the real world. Now we're going to compare it to flat Earth and globe Earth predictions. Now, the math is going to get really ugly. I'm not going to go through the math here. It involves a lot of trig. But basically, if you take a look at do a lot of trig, mostly using sine and then also arc sine or inverse sine, you can estimate the angle of sunrise or sunset. If the Earth were flat, the math is a little bit easier because you just have one 3-sided triangle, so you could just use the law of cosines to figure out your azimuth of sunrise or sunset. All right. Because the math is so complicated, what I've done is I've plugged it all into a spreadsheet. And what the spreadsheet will do is all you have to do is input your latitude and then the time of sunrise and sunset. So with those 3 pieces of information, it will calculate the azimuth of sunrise and sunset using globe Earth math or using flat Earth math. All right. Now, there are some assumptions built into this calculator. On the globe, it assumes that there's no atmosphere and thus no refraction. It assumes that the sun is a point light source, which clearly it is not. So there are some assumptions so that the math is not astronomically correct. It is very homegrown, but you do get within a couple degrees. The flat Earth assumptions are that the sun circles the North Pole exactly once every 24 hours, and that perspective, we all know about perspective. Well, perspective may change the apparent vertical location of the sun, meaning the sun may appear higher or lower in the sky because of perspective, but there's no horizontal displacement. Because if there were horizontal displacement, that would change the azimuth, right? So I've never heard anybody argue that perspective makes things shift to the left or to the right. All right. Now, if you take a look at these numbers, now again, these are from my location at 40 degrees north latitude, and your mileage may vary, but my prediction, it's a full 20 degrees difference between the globe Earth prediction and the flat Earth prediction, and that's going to be very readily apparent when I get out there in the field and actually measure this stuff with my tools. Now, I get accused of copying. In fact, a lot of people get accused of copying stuff. Oh, you just copy what you've been told. Now, I've been at this for well over 10 years. I got started in March of 2008. Got started in the flat Earth debate. And I have never, to this date, I have never heard anybody talk about azimuth of sunrise or sunset as part of a thing that you can explore. The only thing I hear people talk about is sunrise and sunset on the equinox, but I've never heard of people talking about any other date, or especially not how to derive the math. So all the math that I've done is 100% derived by me using just high school geometry, using a piece of scratch paper and a pencil. I just figured this stuff out myself. You're welcome to check my math. You're welcome to see if I made any mistakes. It's all homegrown math. I did not copy this from anybody. So please think about that the next time you accuse somebody of just copying. Alrighty. The third exploration is on the path of the sun in the sky using a sundial. Okay. Now, sundials are easy to construct. I mean, you could buy a professional sundial, and there's actually a bunch of different varieties. They all have different types of gnomons. But the simplest, you jam a toothpick in a pizza box. Now, I don't really recommend this because a pizza box, I mean, unless you really secure it down to a surface, like tape it down to a table or something and have that table be, like a picnic table that's not going to move. But the idea is that the sun's going to be in the sky and you're going to be marking shadows all day. Now, if the Earth were a globe, we have what's called a conic section. All right, and now a conic section is when you take a plane, for example, that yellow square. If you take a plane and you intersect it with a cone. Now, on this illustration, I hope you see those red dots. Those are where sort of the edges are, the vertexes. Those are not going to be equally spaced. All right, on this conic section, those are not going to be equally spaced. The tick marks are going to be spaced further apart at sunrise and sunset. Now, this is actually a little bit more of a technical drawing, but you see that is clearly, it is not a section of a circle. That red line is not a piece of a circle. It is a hyperbola, and the tick marks are going to be further spaced apart closest to sunrise and sunset. And I actually tried this out on a model globe with an actual lamp and the toothpick, and you could see that that's clearly not a piece of a circle, and it is the tick marks are unequally spaced. Now, on the flat Earth model, because the sun is traveling in a plane parallel to the plane of the flat Earth, the sun's going to be doing a perfect circle, so it should trace a perfect circular pattern of shadows on the ground. All right, and not only that, but since the sun is traveling at a constant speed, these pattern of shadows will also be evenly spaced. All right, and again, I tried this out with my Gleason's map, and I mapped it out, and again, that is clearly a piece of a circle, and the marks are evenly spaced. All right, so again, if the Earth were flat, you're going to get a portion of a circle and with regularly spaced marks. Globe Earth, you're going to have a conic section or a hyperbola with unequally spaced marks, spaced further apart near sunrise and sunset. Now, the last two explorations, you technically can do any day of the year, but I figured if you're out there in the field gathering all this data, catching some sun, wouldn't it be nice to just have a couple more measurements that you can make? And actually, both of these things you can measure with the exact same tool, and that is a pinhole solar observer. So a pinhole solar observer you can make just using some cardboard. So I took a long Amazon box. This box was actually the box that my Gleason's map was shipped to me. So it was a very, very long box, but you could easily just take some scratch cardboard and fold it into a tube. Cover one side with foil. Now, one mistake I made was that the foil was still shiny on the inside. So if I were doing this again, I would spray paint the inside of the foil black so it doesn't have any reflectivity on the inside. So you could see those white spots. That's because of the reflections. But basically, you're going to make, essentially, it's a pinhole camera without the film. Instead of film, you're going to use just a piece of graph paper. So you can very carefully record both the size, the apparent size of the sun, as well as the apparent speed. But I'm getting ahead of myself. Another thing you can use is something like welder's glass. You can get this at any decent hardware store. Or you can use solar film if you have solar film that's a little bit more expensive. Whatever you do, don't stare at the sun and don't point your camera at the sun, without any kind of protection. So what the welder's glass will do is it'll cut out the glare, and you'll see a nice crisp edge. I mean, the sun should look like it has a really sharp edge. If the sun does not look like it has a sharp edge, either to your eye or in your camera, if it has a blurry edge at all, then you're not cutting out the glare. Okay. Now with this, the globe Earth model says that the sun's about the same distance away at noon and at sunrise and sunset. It's still approximately 93 million miles away. So the sun should therefore appear to be the same size. On the flat Earth model, the sun is local. The sun is literally just traveling above the plane of the flat Earth. And I wrote 3,000 miles. You could pick any number of miles you want, but the point is that the sun is local, which means the sun is traveling towards the observer or away from the observer on the flat Earth. And you can actually just do the math, which I've done. And I've picked a location in southern Missouri, just arbitrarily, and the ratio of the size of the sun should appear about 2 times bigger at solar noon than at sunrise or sunset. So that's a very distinctive size change difference. So how much bigger will the noontime sun be? So using this map, you see that down in Australia, it may be 3 times bigger. Maybe if you're in the northern reaches of Canada, maybe it's only 1 point something times bigger. But for most observers, it will appear significantly bigger at solar noon. All right. So again, your results: if the sun appears larger at solar noon, significantly larger at solar noon, not just 1 pixel, but significantly larger, that supports flat Earth. If the diameter is the same, that supports the globe Earth model. And lastly, we're going to talk about the speed of the sun, and we're going to use the exact same tool. All right, the speed of the sun in the sky. So again, you can use this pinhole solar observer, but this time you're going to be taking photographs. You're going to be very careful not to disturb your solar observer, but you're going to be taking photographs. So for example, if you take photographs exactly 10 minutes apart, then you can just run the math, right? Run the math and figure out what the speed is. And you can say like the speed is, say, inches per hour or something like that. Like on my solar chronometer, it traveled 7.829 inches per hour. Now that number doesn't mean anything to you, but it will mean something to me because I'm going to be recording the speed of the sun at another time of day. Okay, so whether it's near sunrise, near solar noon, near sunset, those numbers will be meaningful to me because I'm using the same solar chronometer, even though those numbers might not mean anything to you. So again, the more often you record this, the better. I mean, record it at least twice. Solar noon versus near sunrise and sunset. Now again, on the globe Earth model, the sunrise and sunset is really just an illusion. It's because the globe Earth is turning on its axis. So therefore, the sun is not actually getting closer to us or further away. Therefore, it should travel the same approximate 15 degrees per hour all day. If the Earth were flat, we can use the law of perspective. Again, this observer looking at this race car coming by, the race car is traveling at a constant speed. You could just imagine that's the sun in the sky. But when the sun is further away from you, it's going to be moving at a smaller angle. Okay, slower apparent speed. If the sun is closer to you, like for example directly overhead, or close to directly overhead, say solar noon, it's going to be subtending a larger angle. And again, I've run the math, and you can see that these angles, again, taken from Missouri, the angle is larger near solar noon, the angle is smaller near sunset. Okay, and again, you could run the math. I've done the math for you. And this is an example. Now, remember, we said 15 degrees per hour at on the globe. Well, here at solar noon, it's traveling 23.2 degrees per hour, versus 11 degrees per hour at sunrise and sunset. So for this particular example, and again, your math will be different. For this observer in Missouri, the sun is going to appear to move twice as fast at solar noon in the sky. And that's definitely going to be very obvious if you measure the speed of the sun in the sky. Okay, and again, this is just sort of an overview. Again, folks in Australia, the solar noon sun should be, going about 4.5 times faster. But it will be appreciably faster. Even people in fairly northern latitudes, at least 1.5 times faster, for folks in even the Scandinavian countries. But this will be very, very apparent. If you measure this stuff carefully, you will get a very significant difference in the apparent speed of the sun in the sky. Okay? So those are the 5 explorations. Now, let me give you an analogy. I'm really hoping that you do all 5 explorations, but even if you just do one, you should get some nice data. So let's say there was a bank robbery, and they got 4 clues as to the identity of the bank robber. And these clues were the robber was driving a white pickup truck, was clean-shaven, wearing a big cowboy hat, and then maybe he stepped in some mud outside the bank, and he left a nice footprint that they were able to measure, size 13 boots. Okay, so those are our 4 clues. And let's say circumstances were such that they narrowed it down to 2 suspects, Steve and Nathan. Okay, so let's take a look at the vehicle. Well, Steve drives a black sedan, Nathan drives a white pickup truck. You could argue that Steve might have been driving a white pickup truck on the date of the bank robbery. I mean, so this is not, this one clue does not guarantee Nathan was the bank robber. Okay? Let's say facial hair. Well, Steve has a walrus mustache, whereas Nathan is clean-shaven. And again, maybe Steve used makeup to, hide his mustache. Maybe he pasted his mustache down and used some makeup to cover it. Maybe he shaved off his mustache and then now is wearing a fake mustache. Okay, so, maybe there was some fakery there. Headgear. Steve normally wears a baseball cap. Nathan likes to wear cowboy hats. Again, Steve could have been wearing a cowboy hat on the date of the bank robbery. That is possible. And then footwear. Well, Steve normally wears size 10 sneakers, whereas Nathan wears size 13 boots. And again, let's say Steve were just trying to set up Nathan. Let's say he wanted to rob a bank, but he wanted to set Nathan up as the fall guy. Yeah, Steve could have definitely faked every single one of these clues. Okay, but since we're talking about the natural world, we're not talking about human motivations, right? We're talking about observations you're making out in the natural world. So I could definitely understand how you could explain away one of these clues, but explaining away all of them would be a bit of a stretch. So what are the clues that we're gathering on or around the June solstice? So the first piece of data we gathered was the angle of elevation at solar noon. And if the Earth is a globe, that's going to be 23.4 degrees northward from where it was on the equinox. Whereas on the flat Earth, you're going to have to use a little bit of trig to find the angle of elevation. The azimuth of sunrise and sunset, again, the math gets very complicated, so we're just going to use the spreadsheet. But again, at my location, which is 40 degrees north latitude, I discovered that the globe Earth would predict an azimuth 20 degrees further away from where the flat Earth predicted. So when I go out there in the field, I should be able to get some good data. The path of the sun in the sky via a sundial. Again, if the Earth is a globe, you should get a hyperbolic pattern with unequally spaced marks. If the Earth were flat, you should get a circular pattern with equally spaced marks. And then next we have the apparent size of the sun. The globe, if the Earth were a globe, since the sun is so far away, it should appear the same size all day. Again, use a solar filter or use a pinhole solar observer. If the Earth were flat, the sun should appear significantly bigger, like 1.5 times, 2 times, maybe even 3 times bigger at midday than at sunrise or sunset. The angular speed of the sun. All right, the angular speed, the sun should be moving the same speed across the sky, about 15 degrees per hour all day. Whereas if the Earth were flat, since the sun is a lot closer to the observer at midday, the sun should appear to be moving faster. All right, so those are your 4 clues. Now, like I said, the more clues you gather, the more data you'll have so you can draw a conclusion as to what the shape of the Earth is. And this data is all data you gather out there in the natural world. All right, so I'm not saying, this is just theory. I'm saying get yourself outside and actually record these measurements using the natural world. All right, so would you like to share your results? Oftentimes I propose these do-it-yourself explorations, but people don't really have a medium for sharing the results. So there's a couple different ways. And if you do share your results, you do not have to give away your exact street address, right? So just provide your latitude, specifically north or south latitude. So like, for example, I'm at 40 degrees north latitude, right? So you have several options if you want to share your results. One is to leave a comment below this video, or leave a comment below the video in question. Like there's 5 videos that are linked to with this video. So leave a comment below those. And again, just describe your results. You could send me an email at flatearthmath@gmail.com over the next couple weeks. And again, please let me know if you want to remain anonymous. So I'm going to make a follow-up video in 2 weeks at the end of solstice season, just sharing the results that people shared with me. You could post into our message boards. Now, the message boards are a bit empty at the moment, but the address is flatearthmath.boards.net. Okay, so right now this is what the message boards look like now. But here's a little screenshot, and there's a board on the June solstice observations, and then there's actually 5 subboards. So you could post your results in there. And like I said, there really are no posts there now, so it's a bit empty. So how do you sign into these boards? Well, all you need is an email address, and then you create a password for yourself, and you can type your name. And again, you can use a pseudonym if you like, and then your birthday and gender, and you can feel free to make up a birthday and gender. But the reason why they ask for your birthday is because they don't want little children to be logging in. Okay, pretty straightforward. Now the last thing I'm going to say is I do have a Patreon account, and I genuinely appreciate all the support that I've received over the years, both financial as well as moral support. The whole community has been really great in supporting me and my channel. I do this, it's sort of a labor of love, but with greater financial resources, I'll be encouraged to make more videos. So please consider supporting me on Patreon. And I do have some perks, like for example, some behind the scenes stuff for members. Now, Brian Tracy reminds us that there are no limits to what you can accomplish except the limits you place on your own thinking. So again, lastly, I would just want to encourage you again, please go outside and make some measurements this June solstice season. It doesn't have to be the date of the solstice. You can go, say up through July 4th. Within 2 weeks of the June solstice, we'll give you pretty decent results. And then whatever you do, when you do your explorations, whether you do 1 exploration or more, please share your results. Your comments are welcome, as always, and please be kind to each other. Thank you so much. Bye-bye.